So I want to talk about section 2.3, which is functions. And I'll probably split this into two videos because when I did this whole thing as one video, it messed up, and I wonder if it wasn't because it was just too long or something. 9, 17, 27, 29, because I'm just recording directly to my iPad. So the topics for this section are function, of course, domain, codomain, range, inverse, then we're going to have one-to-one, onto, bijection, factorial, and floor. So I'm going to define a function for you. A function is, function f from a set A to a set B is an assignment of every element in A to exactly one element in B. Now I want to pause here and say, when you've probably seen functions defined before in some sense before this class. So if you were to misread this sentence, you could interpret it as every element in A is mapped to the same element of B. And that is a kind of function called a constant function, but that is not what a function is in general. So I'm intentionally using this somewhat loose language to highlight how imprecise natural language can be, even when by context we're pretty sure that's not the meaning. You need to be really careful when you're communicating about precise things with imprecise language. We write f maps A to B with f of A equals B, or, and here's some new notation, probably a lot of you have not seen this before, f takes little a to little b, and this is a vertical bar with a right arrow next to it. This is the maps to symbol. So this and this are equivalent. They're just, you normally see f of a equals b. You've probably seen that before this class, but this is another equivalent notation. This just tells us what the function's sets are, and that I want you to think like a prototype of a function in computer programming. All right, so the set A is called the domain. The set B is called, I'll pause to take a sip of tea while you guess, the codomain, or target. The subset, and some of you are like, wait, he meant range. He misspelled range. No, the subset of B that is mapped to by F is called the codomain. Sorry, not the codomain. It's the whole point I'm trying to make. Is called the range or image of F. So this is of F, not off. Of F. Okay, the range of F or the image of F. So you've probably heard this set called the range. That set contains the range. It might be the range depending on your function, but it also might not be the range. There might be elements in B that are not mapped to, in which case we need a separate name for that set, which we're going to call codomain or target. The graph of F is the set of ordered pairs a comma b such that f of a equals b, and this is going to be a subset of the Cartesian product of a with b. This is the graph of f. Okay? So let's take a minute and go after this domain and range and codomain stuff. Let's consider the function f, which maps the real numbers to the real numbers. So this means it takes real numbers as inputs and it gives us real numbers as outputs, defined by f takes x to x squared. So this, again, you can read this as f of x equals x squared. Well, let me just quickly sketch a graph. I don't know why let's just sketch. And we've got a parabola. Now, if you're not an expert on graphing polynomials and stuff, it's not a huge deal. We're not going to do a whole lot of like really esoteric stuff, but you should know at least that the graph of f of x equals x squared looks like a parabola. And we notice that these negative outputs are never used. So they're not in the range. This part up here, that is the half open interval from 0 to infinity, actually would that be a closed interval? I mean, I don't know. The interval including 0 and going up towards infinity is the range. But, you know, we said that the format of the outputs was a real number, but that doesn't mean that all real numbers are attained in the outputs. That's kind of the point of that. All right, let's move on and do some function arithmetic. So let's say given two functions, f and g. I'm so fond of just butchering the innocent little ampersand. Given two functions, f and g, we write f plus g of x to mean f of x plus g of x. Just really squeezing that in there. We write, that's garbage. I'm sorry. I need to move that. I tried so hard. F of x plus g of x. We write fg of x to mean f of x times g of x. And something that you may not have seen is we write f little circle g of x to mean f of g of x. And I'm just going to add a note here. When the respective domains make sense. Because you could have, you know, if f was square root and g was, you know, something that spit out some negative numbers, then you might end up with some complex numbers, right? So you have to be a little careful. And you want to make sure that things are defined, but I'm not going to go too far down that path. But I just want to say that this is a thing we need to worry about. And I'll say if f little circle g of x equals g little circle f of x equals x, then f and g are inverses. And we write f equals g raised to the minus 1, or g equals f raised to the minus 1, or both. All right, let's do a couple of quick examples. Let's do f of x equals 2x plus 1, g of x equals x minus 1 over 2. Let's do h of x equals x squared. Let's compute a few different things here. Let's compute f plus g of x, fg of x, f composed with g of x, g composed with f of x. Let's do f h of x. Oh, and I should say similarly, we can do f minus g or f divided by g. But in the division case, we need to make sure that we're not dividing by 0. That's all. Let's do f composed with h of x, and let's do h composed with f of x. I know this is a lot of things, but they should go relatively quickly. So this is going to be f of x plus g of x, and this is just 2x plus 1 plus x minus 1 over 2. And if we were to simplify this, I think we'd end up with 5x plus 1 over 2. Okay, f times g of x, that would be 2x plus 1. You know, that's okay. X minus 1 over 2. I was going to say, this one's going to be ugly. I want to skip it, but whatever. This is going to be, I'm going to pull the 1/2 out front. And we're going to have 2x squared, let's see, plus x minus 2x, so minus x, and then minus 1. That seems about right. I've got what? 2x squared plus x minus 2x plus, yeah, there you go. That's fine. F composed with g. Here's the key point. This is f of g of x. So what is f of g of x? Well, we're going to do, f takes whatever the input is, multiplies it by 2 and adds 1. In this case, the input is g of x. So it's 2 times g of x plus 1, right? So this is 2 times x minus 1 over 2 plus 1, which equals x, right? To do g of f of x, this is g of whatever the input is. So what do we do with g of x? G of input is you take the input, subtract 1, divide by 2. So this is, this is f of x minus 1 divided by 2, which is 2x plus 1 minus 1 over 2, which again is x. Okay? Since these two are equal, that means f and g are inverses. All right? Now let's look at f times h just for fun. This is f of x times h of x, which is 2x plus 1 times x squared, and that's just 2x cubed plus x squared. Cool. Now let's do f composed with h. Well, that's f of h of x. Now I've been doing sort of outside in. I've been simplifying the outside and then simplifying the inside. I've been simplifying g then f, or outside then inside. Let's do the inside then the outside. So this is f of h of x. Well, what's h of x? H of x is x squared, so this becomes f of x squared. So I'm simplifying the inside first, or plugging in the inside first. So what does f do to x squared? Well, it multiplies it by 2 and adds 1. So it's 2x squared plus 1. Now let's look at h of f of x. H of f of x is h of 2x plus 1, which is 2x plus 1 quantity squared, which is going to be 4x squared plus 4x plus 1. Notice these are not equal, so f and h are not inverses. We've got a fair amount more, but I think I'm going to cut it early here because, like I said, I was having some issues with my iPad recording.